Good morning, everyone. I hope you guys are doing well. This is section 3.4 out of our textbook, Linear and Angular Speed. And I'll try to go at a fairly smooth pace, but you can always rewatch this either on the YouTube channel or on Edmodo. All right, so we're talking about speed. I want to bring you back to maybe 6th grade, 5th grade with this little equation right here. Do you remember D equals RT, dirt? Sometimes some of the teachers used to call it back in the day. Distance equals rate times time. Rate, we often talk about in terms of speed. So if I wanted to rearrange this formula, I can rearrange this formula to say that ultimately rate is equal to distance divided by time. Now today's formula, although we're dealing with angles and and circles, really we're going to be basing everything off of this formula right here. So I'm going to start by giving you a nice little circle, on an axis. Here we go, right? This is our radius, and I'm going to put some point P here. I'm going to call that point P, and I'm going to draw a ray to point P, and at my origin is O. Now, if you can imagine this point P, if right here we know that this distance is S being our arc length, I don't know if you remember that, but our arc length. Now if I were to talk about this point P, and if it was moving in a counterclockwise direction, and I want to talk about how fast this point is moving around the circle, that's linear speed. So let's write that down. Linear speed is really just the measure of how fast the position of point P is changing. So how fast that position where point P is, how fast P is changing. So I'm going to underline position of P. Now, the formula is as follows. So here's a formula for linear speed. So we've got, instead of using R for rate, just like in trig, in calculus also, in physics and calculus, we use V for linear speed. So I'm going to write underneath, this is linear speed. V also you may recognize as velocity. Velocity is linear speed. It doesn't have direction to it. Acceleration, if you're taking physics right now, acceleration is speed with direction. So V for velocity. V equals S, the arc length. So this is our distance. So here's rate, speed, S being our arc length, and let's just go ahead and write that there. Arc length divided by time, T time. So in disguise, I'm hoping you're able to see this, that in disguise, this is really R equals dt. Speed equals the length, the actual distance that this point is traveling. This point is traveling in a circle, so we're talking about the arc length, divided by the time. Now something that's really key to distinguish between linear speed, which we're looking at now, and the next angular speed has to do with the units. This is measured, if we're talking about arc length is often given in inches or in feet, divided by time, so often in seconds, because things are moving usually very quickly. So I want you to focus on the fact that if you see inches per time, centimeters per second, feet per second, that this is a linear speed, it's a velocity, okay? All right, let's discuss what angular speed is. We'll define it, and then I'll give you some problems to work with. So here's angular speed. Angular speed has to do with, guess, angles, angular speed. So angular speed is really just the measure of how fast angle, and I'm going to specify, and actually I'm going to put back a point right here, B. So angle POB, or often our theta, maybe we should put theta there. I'll put in parentheses theta, is changing or changes. So I'm going to underline angle. Angular speed, how fast the angle is changing. The angle is changing. Now here's the formula for angular speed. Angular speed actually uses a Greek letter and it kind of looks like a W. Often the tips are kind of touched together. This is omega, by the way. That's lowercase omega. Omega, this is your angular speed. The symbol for angular speed. So omega equals the actual angle divided by time. So in parentheses, I'm going to write central angle. Our theta is central angle divided by our time, usually again in seconds. So angular speed is how fast the angle itself is changing in relation to the time. So if you can imagine, has to do with the units we'd be using is our angle divided by seconds. Now, just like previously when we dealt with our arc lengths, omega needs to be in radians. So this is in radians. So I'm going to write radians per time or second would kind of be our units. So I'm going to box our units. We only work in radians. So if you need to put that on side, only in radians. Okay, only in radians. So if you're given something that, if you're not sure if you're using linear speed or angular speed by the question, look at what units are being offered. Is it, pi over 6 radians per second, or are you being told that something's changing 35 centimeters per second? If it's 35 centimeters per second, you're working in linear speed. If it's some type of radians per second or degrees per second, which you'd have to change to radians, you're looking at angular speed. Now there is a relationship between these two, and I want you to see the relationship between the two. So here's the relation between linear and angular speed. Okay, so here's the relationship. And again, we're deriving these formulas. I want you to meet these formulas. So do you remember, let's go back to arc length and theta. So let's go back to just radians. Do you remember how radians were, the way we defined radians was the arc length divided by the radius, right? How the arc length, let's go back over here, was how long this was in relation to the radius, right? And this looks almost like 1 radian, for example. And then we can take this formula and we can rearrange it to solve for arc length. So I can go ahead and rearrange this to say that the arc length is really just the radius times my angle. And we played with this, I believe, in 3.2. Now, if I go back to my linear speed formula, so this formula right here, I'm going to write my linear speed formula, v equals s over t. Velocity is equal to the arc length, how far I'm traveling divided by the time. I can then actually do some substitution here and say, well, my arc length is really r times my theta divided by t, right? I'm just using substitution here, that the arc length is really the radius times the angle divided by my time. And then if you notice, going back here, check this out. Isn't omega angular speed theta over t? Well, here's theta over t. I want you to be able to see, just with basic fractions, I can separate this out. So we ended up getting that the radius times omega, so the radius times the angular speed, is actually linear speed. So I'm going to write this in a cleaner way. V equals radius times omega. Linear speed, let's write it maybe down here. Linear speed is equal to the radius of your circle, of your gear, of your wheel, times your angular speed. That's the relationship, and you can see the derivation of that relationship. So let's kind of summarize this all. So I'm going to turn the page, and I want to have us summarize all of our new formulas. So we have angular speed and our linear speed. Our angular speed, once again, is omega. So our angular speed is equal to radians per second, radians per time. The angle, the rate at which the angle is changing per time. That's how fast our angle is changing. Linear speed, we had this formula. The angular speed is just the distance that the point is traveling over time. So the arc length divided by time. We then have that angular speed. We're replacing our arc length with the radius times theta over t. I'm using my substitution. So I could work with that information. Or lastly, I know that how fast a point is traveling is related to the radius times how fast the angle is changing. So these are going to be kind of the 4 general formulas that we're going to be working with. Okay. The next thing I want to do is I want to walk you through, and I'm going to move this down, I want to walk you through an example in the book, because I think the very first example students may struggle with how they're doing this. So the first question says, maybe I'll just write this down, says suppose that point P is on a circle with, and I'm going to abbreviate, with radius 10 centimeters, and ray OP is rotating with an angular speed pi over 18 radians per second. Now, if you're interested, this is the example number 1. I am taking this straight out of the book. I want you to be able to see how they're doing this in the book on page 118. So I'm taking this straight out of the book because I think sometimes students get stuck reading the textbook. So the first question that you're asked, first of all, let's maybe summarize, before we even look at the question, let's summarize what we know. We're given radius 10 centimeters. So I'm going to recap. I've got radius of 10 centimeters. That I know. I'm then even told that I've got an angular speed of pi over 18 radians per second. Angular speed is which variable? That's omega. Omega is pi over 18 radians per second. In 1 second, it's traveling pi over 18 radians. So this is what we know. Okay, so working with that. First question is, find the angle generated by P, generated by point P, in 6 seconds. Okay, that's the key. In 6 seconds. They want to know the angle that's created in 6 seconds. Now, before you go racing off to your formulas, let's think about this. We know that this point, and I'm just going to draw a random picture. Here's O, here's P. This is not drawn to scale. I'm told that this is traveling, the angle is changing pi over 18 radians in 1 second. So the question is asking, what angle is created in 6 seconds? I know that it's going pi over 18 in 1 second. So in 6 seconds, all I'd have to do is multiply by 6. I want to know what's happening in 6 seconds. So pi over, so we end up, let's just simplify, 6 pi over 18. This can be reduced to what, pi over 3? So it is in 6 seconds, our theta, this is now theta, our angle generated is pi over 3. So we're looking at a 60-degree angle in 6 seconds. Okay, not too scary so far, I'm hoping. Second question of the same type says, find the distance traveled. Find the distance traveled by P in the 6 seconds along the circle. We're assuming it's along the circle. So in the 6 seconds, how far has this point traveled? How far has this point traveled? Well, let's go back up to our formulas. We know theta. We know our time. Right? We know that we've traveled 6 seconds. We know our theta, but we ultimately we're looking for, what variable are we looking for? We're looking for s. We want to know the distance traveled. So maybe one thing that we should write above here is just to recap that s equals r times theta. That's the other one we're working with. Arc length, the arc length is related to the radius times the angle. So in 6 seconds, what is the angle that this point has created? In 6 seconds, our angle, our theta, is pi over 3 radians in 6 seconds. And we want to know, so we know our angle, we know the radius. Our radius is what? We were told it was 7 centimeters. So if I want to know how far it's traveled, I'm using this formula, s equals r theta. So I have, just quickly, pi over 3 times 10 is giving me my arc length. And let me raise that up for you. So ultimately, we find out that in 6 seconds, and this was in centimeters, right? This is centimeters. In 6 seconds, this point has traveled 10 pi over 3. Now that's exact. If you wanted to punch that into the calculator and find out really how many centimeters we're talking about, we're looking at 10 times 3.14 divided by 3, so, 11-ish or something. Okay? Last type of question that you're asked on this type of problem is asking now, find the linear speed. Find the linear speed of the point. How fast is that point traveling around the circle? So if we know our velocity, no, we're looking for a velocity, aren't we, right? That's our velocity. We're looking for a velocity. Going back here, we can use a variety of these formulas, but we know how far it's traveled in 6 seconds. We know, right, we know it's traveled 10 pi over 3 in 6 seconds. We know the time, it's 6 seconds, so we can find how fast it's traveling in 1 second. So 10 pi over 3 centimeters is how far it's traveled in the 6 seconds. And just to recap how to do complex fractions, right? That's 6 over 1, we flip, we get 10 pi over 3 times 1 over 6. We can do some cross-canceling, and we end up with, if you do some cross-canceling, 5, 3, we get 5 pi over 9. And what are our units? Centimeters per second. Linear speed, how far has it traveled in 1 second? So that's one type of problem you're going to see, and that's actually, that's probably somewhat as tricky as it comes. All right, then we have types of problems that are a little bit more chug and plug. So for example, let's do something like, let's call this example number 2. I forgot to call that other one example number 1. Says they'll actually tell you which formula to use. Use omega equals theta over t to find the missing variable. So they're going to tell you, for example, omega is 4 pi over 3 radians per second. And then they're going to say, hey, and also time is 30 seconds. So I've given you a few of these plug and chug type problems where, what are we looking for? We're looking for theta. So if we were to plug into this formula, we have 4 pi over 3 radians per second equals our unknown over 30. Multiply both sides by 30, yes. Then we have theta equals, what, 40 pi radians? I think it's really important to keep your units so you remember kind of what's going on, what we're looking for. So that's kind of an easy problem. And then the last type of example I'm going to give before I send you off is a problem like this. Find omega, find the angular speed for the hour hand of a clock. I think I gave you one problem like this on your homework, but I think this is kind of an interesting problem. So we're looking for ultimately how fast is the angle changing of the hour hand of a clock. So let's use, we have omega equals theta over t. I mean, that's our basic angular speed. So first off, we have an hour hand of a clock. So maybe we should calculate in 1 hour. Maybe that will be our rate, our time. In 1 hour, what angle is the hour hand creating? Now think about the angle in which in 1 hour, the angle in which that's creating. So let's do this. If you're stuck, we've got 3, 12, 1, and 2, right? So can you think of this in terms of this is a 90-degree angle? What's this angle? What's one of these angles? What's one of these angles right here? We've divided 90 degrees into 3 equal parts. So each of those angles is 30 degrees. So in 1 hour, it's a 30-degree angle, but we need it in radians. So 30 degrees in radians is what? Pi over, yes, you're right, 6. I'm assuming you said that. So in 1 hour, here's our speed, this is radians. In 1 hour, and since we already have a base unit of 1, we have pi over 6 radians per hour. This is how fast the hour hand of a clock travels. All right, good luck. Use Edmodo over the weekend, and I can answer a whole bunch of questions. Good luck, guys, and I will also leave the solution manual so that you can take a peek. Have a great weekend.